Spectroscopy. In this chapter, I will be discussing on a spectroscopic technique and how it is used for finding out the structure of molecules. Now, we cannot see atoms and molecules directly, but we can know the interaction of atoms and molecules with electromagnetic radiations. And from the analysis of this interaction, we can know about the functional groups and the determination of a structure of organic compounds. So, spectroscopy is a study of interaction of electromagnetic radiation with matter, and this has been used for analysis of functional groups and determination of structure of organic compounds. Depending upon the techniques used, there are different types of spectroscopy, which include microwave spectroscopy, ultraviolet visible or UV visible spectroscopy, infrared spectroscopy, NMR spectroscopy, and mass spectroscopy. I will be discussing among this UV visible spectroscopy. The spectroscopic techniques have several advantages, and they are very quick and sensitive. Very small quantities of the sample is enough for taking spectra, and even this small quantity can be recovered after the analysis is over. The measurements are highly reliable in establishing the identity of the compounds. The information obtained in these measurements are in the form of a permanent record. That is, you can refer it later on for comparison of some unknown compounds. And continuous operation is also possible. This is when you are applying it in industry. For example, in industry involving synthesis of chemicals, the samples can be analyzed during the process of synthesis and can be automated also. Usually these are very cheap. So before going into the spectroscopic technique, we have to know what is the nature of electromagnetic radiation? What is the characteristic of electromagnetic radiation? Electromagnetic radiation consists of oscillating electric and magnetic field which are oscillating perpendicular to each other as well as to the direction of propagation. So this is the direction of propagation. So direction of propagation is direction in which the wave is moving. And perpendicular to this direction of propagation, you have oscillating electric and magnetic fields. So E is the electric field. The red colored ones are the electric field. You can see it is oscillating. And B is the magnetic field. The blue colored one is the magnetic field. And these are oscillating perpendicular to each other, and they are also perpendicular to the direction of propagation. So this description is regarding the wave nature of radiation. So radiation has wave nature and it has oscillating electric and magnetic field which are perpendicular to each other and also perpendicular to the direction of propagation. So when you have a wave nature, these are characterized by certain parameters. The parameters are, first one is wavelength, which is represented by the symbol lambda. Wavelength is the distance between two adjacent crests or troughs. So this is a crest, this is another crest. The distance between the two adjacent crests is lambda. This is a trough, this is another trough. The distance between these two is also lambda. The SI unit is meter. It is also expressed in terms of nanometers or Armstrong. 1 nanometer is 10 raised to minus 9 meters and 1 Armstrong is 10 raised to minus 10 meters. The next parameter is frequency, represented by nu. It is the number of waves that pass through a point in 1 second. And the SI unit is second raised to minus 1. It is also expressed as hertz. Short form is Hz. Next is wave number. It is the reciprocal of wavelength expressed in centimeters, or it is the total number of waves that passed through a space in 1 centimeter. It is written as nu bar, and nu bar is equal to 1 by lambda. If lambda is in meters, then nu bar will be in meter inverse. If lambda is in centimeters, then nu bar will be in centimeters inverse. Usually in problems, wave number is expressed in terms of centimeter inverse. So, lambda is equal to 1 by nu bar. Next is velocity. It is the distance travelled by the wave in a unit time. And velocity of electromagnetic radiation in vacuum is a constant, and it has the value 3 into 10 raised to 8 meters per second, or 3 into 10 raised to 10 centimeters per second. Now C is related to lambda and nu, as C is equal to nu lambda, or nu is equal to C by lambda. Now since C is a constant, we can say nu is inversely proportional to lambda. That is, higher the frequency, lower will be the wavelength, and vice versa. Now this much was regarding the wave nature of radiation. But it is proposed that radiation also has particle nature, and according to which light is considered as packets of energy called quanta, and energy is given by expression E is equal to h nu. And since nu is equal to C by lambda, E is equal to h C by lambda. Now what all you have to remember? Remember that nu bar is equal to 1 by lambda, or lambda is equal to 1 by nu bar. C is equal to nu lambda, or nu is equal to C by lambda, or lambda is equal to C by nu. Now since nu is equal to C by lambda, this can be written as C into 1 by lambda. 1 by lambda is nu bar, this is C nu bar. So nu is equal to C nu bar, or nu bar is equal to nu divided by C, or C is equal to nu divided by nu bar. Lambda wavelength can be expressed in terms of Armstrong, nanometers, millimicron, micron, millimeters, or meters. So 1 Armstrong is equal to 10 raised to minus 10 meters, which is equal to 10 raised to minus 8 into 10 raised to minus 2 meters. Minus 2 is given prefix centi. So this is equal to 10 raised to minus 8 centimeter. 1 micron is equal to 10 raised to minus 6 meters, which is equal to 10 raised to minus 4 centimeters. Now how we can write the relation between Armstrong, millimicron and micron? So 1 Armstrong is equal to 10 raised to minus 10 meters, which is equal to 10 raised to minus 4 into 10 raised to minus 6 meters. 10 raised to minus 6 meters is micron. So this is 10 raised to minus 4 micron. Now this is equal to 10 raised to minus 1 into 10 raised to minus 3 micron. 10 raised to minus 3 is given as prefix milli. You know 1 millimeter is equal to 10 raised to minus 3 meters. So 10 raised to minus 3 is given prefix milli. In the same way here also it is written as milli. So this is equal to 10 raised to minus 1 millimicron. Next is 1 nanometer is equal to 10 raised to minus 9 meters, which is equal to 10 raised to minus 7 centimeters. 1 millimicron is equal to 10 raised to minus 3 micron. So 1 micron is equal to 10 raised to 3 millimicron. Now 1 millimicron is equal to, milli can be written as 10 raised to minus 3 and micron can be written as 10 raised to minus 6 meters. So this is 10 raised to minus 9 meters and 10 raised to minus 9 meters is nanometer. So 1 nanometer. So instead of millimicron we can write as nanometer. So this is equal to 10 raised to 3 nanometers. Now 1 Armstrong is equal to 10 raised to minus 10 meters, which is equal to 10 raised to minus 1 into 10 raised to minus 9 meters. 10 raised to minus 9 is given prefix nano. So this is 10 raised to minus 1 nanometers. So 1 Armstrong is 10 raised to minus 1 nanometers, or 1 nanometer is equal to 10 Armstrong. And 1 nanometer is equal to 1 millimicron. This I have already explained. And instead of milli we can write 10 raised to minus 3. So this is equal to 10 raised to minus 3 micron. Remember, mu is equal to micron. There are different types of electromagnetic radiations. And the arrangement of these different types of electromagnetic radiations in the order of increasing wavelengths or decreasing frequency is known as electromagnetic spectrum. This is the arrangement of the electromagnetic radiations in increasing wavelength, lambda, from left to right, and from right to left they are arranged in increasing frequency. As I said earlier, frequency is inversely proportional to wavelength. And the energy of these electromagnetic radiations is given by the expression E is equal to h nu. So as frequency increases, energy also increases. Since nu is equal to c by lambda, E is equal to h c by lambda. So as lambda increases, energy decreases. So frequency is increasing in this direction. So these are high energy radiations. So gamma ray is high energy radiation and radio waves are low energy radiation. So the arrangement of the different electromagnetic radiations are gamma ray, X-ray, UV, visible, IR, microwave and radio waves. Radio waves have the longest wavelength, lowest frequency, so lowest energy. Gamma rays have highest frequency, smallest wavelength and high energy. So gamma rays are high energy radiations. And here you have the visible region which is expanded here. This contains the VIBGYOR, or the 7 colors. Now how is the spectrum generated? If the white light in the visible region is passed through a prism, it gets dispersed into the different wavelengths, and what we are getting is a dispersed light, which is the spectrum, which is ranging from violet, indigo, blue, green, yellow, orange, red. And this is continuous. One color is fading into another. Now, spectroscopy deals with interaction of this electromagnetic radiation with matter. And how does it interact with matter? So for this, recollect the hydrogen spectrum. There are two types of hydrogen spectrum. One is the absorption spectrum and other one is the emission spectrum. In absorption spectrum, when light is given to an atom where the electron is in the ground state, the electron can take up the energy from the radiation and go to the excited state. And the energy taken up by the electron to go from the ground state E1 to the excited state is equal to E2 minus E1, which is equal to h nu. H nu is the energy of the photon or light absorbed. And if the remaining light is passed through a prism and if it is dispersed, we can see that in the region where the radiations are absorbed, there are dark lines. So these are the lines, or these are the radiations which are absorbed by the atom. And what we are getting is the spectrum of hydrogen atom, and this is the absorption spectrum. And if by some means the atom is excited to a high energy level, it can be by thermal means or by light. So here the electron is in the high energy level, and an electron in the high energy level is not stable. It has to fall back to the lower energy level, and during that process energy is emitted. And this emitted radiation, if it is passed through a prism and dispersed, we can see that there are certain lines which are corresponding to the emitted radiation, and the light and the energy of the emitted radiation will be equal to the difference between the energy levels E2 minus E1, and which is equal to h nu. So this is an emission spectrum. So we can see that in the absorption spectrum there are dark lines in a bright background, and in emission spectrum the background is dark but the lines are bright. But what you have learned now is the atomic spectrum. Now next we will be dealing with molecular spectroscopy. In atoms, the transition is taking place between the different electronic energy levels present in an atom. When we deal with molecular spectroscopy, the transition is taking place between the different electronic energy levels present in a molecule. We will see that later on. So if E1 is the energy of the lower energy level and E2 is the energy of the higher energy level, then when a molecule is exposed to an electromagnetic radiation, it gains energy, and the energy gained delta E, which is E2 minus E1, will be equal to h nu, where nu is the frequency of the absorbed radiation and h is the Planck's constant. H has the value 6.6242 into 10 raised to minus 34 joules second. So we can see that higher the frequency, more is the energy gained by the molecule. And since frequency is inversely proportional to wavelength, shorter the wavelength of the radiation, more energetic is the radiation. So when a molecule is exposed to a source of energy, some of the molecules gain energy and get excited from the ground state to the excited state, and the energy absorbed will be equal to delta E, which is equal to h nu, and since nu is equal to c by lambda, this is equal to hc by lambda. Energy absorbed per mole is equal to Na into hc by lambda, where Na is the Avogadro number. So this is the energy of one photon and this is the energy of 1 mole of photon absorbed, where H is equal to 6.6242 into 10 raised to minus 34 joules second. C is equal to 3 into 10 raised to 8 meters per second, and Na, the Avogadro number, is equal to 6.02 into 10 raised to 23 per mole. That is 1 mole contains 6.02 into 10 raised to 23 particles or photons. So energy absorbed per mole, which is equal to Na hc by lambda, is equal to Na is 6.02 into 10 raised to 23 per mole. H is 6.63 into 10 raised to minus 34 joules second, into C is 3 into 10 raised to 8 meters per second, divided by lambda expressed in nanometers into 10 raised to minus 9 meters. Here the lambda value is expressed in nanometers. So if lambda is 286 nanometers, here it will be 286 into 10 raised to minus 9. Here second and second raised to minus 1 will get cancelled. Meter and meter will get cancelled. And this value will become 2.86 into 4.18 into 10 raised to 7 divided by lambda value expressed in terms of nanometers, joules per mole. Now if lambda is equal to 286 nanometers, then energy is equal to 2.86 into 4.18 into 10 raised to 7 divided by 286. You just have to substitute the value 286, since we have already taken into account the 10 raised to minus 9 factor during derivation of this expression. This many joules per mole. This is equal to 4.18 into 10 raised to 5 joules per mole. And this is nothing but 100 kilocalories per mole. So absorption of 4.18 into 10 raised to 5 joules per mole, or 100 kilocalories per mole, or absorption at 286 nanometers is sufficient to bring about many chemical reactions. Earlier we saw that atoms have both emission and absorption spectrum. But in molecules like organic compounds, they do not give rise to emission spectra, but they give rise only to absorption spectra, because organic compounds cannot withstand the drastic conditions necessary to stimulate them to emission spectra. That is, If you want to get an emission spectra, you have to get the molecule in the excited state. And from the excited state only, it is coming to the ground state and emitting radiations. This is not possible for molecules. So usually molecules exhibit only absorption spectra and not emission spectra.